a three-dimensional sphere. Select the light tag once again. Efficiency or texture, much like distribution, can accept any shader, or it can load an external image via the image texture node. Go ahead and assign an image texture. And let's give it an external image. In this case, I will use this colorful pattern. And there we go. Let's go back. And if I now reduce the power to something like 1, you'll be able to clearly see how this texture is now mapped across the area light. Let's push the power up to 800. And similarly to the way IES lights work, if I now grab the area light and try rotating it, the image pattern will not follow. To fix this, we need to fix the projection. So let's once again check the image texture node and apply the projection node. Texture projection needs to be set to spherical with a rotation of 90. Now if I grab my light and rotate it, you can see how the illumination changes based on the rotation I apply. In this final example, we'll take a look at using sampling rate. This parameter allows users to choose which light sources will receive more samples. As you can see, I have prepared two identical area lights. Let's select the light tags and set sampling rate of 1. What this means is that the number of samples dedicated to sample light source 1 and light source 2 will be in proportion 1 to 1. If, however, I select the second light source, the one on the right, and set its sampling rate to 2, this means that this light source will get twice the amount of samples compared to the first one. Thus, the image here looks a little bit cleaner. Let's set something extreme like 100, meaning the ratio of samples will be 1 to 100. Thus the dramatic difference in image quality. And before we close this chapter, I'd like to say that there have been quite a few technical terms and definitions that have been intentionally skipped for these demonstrations. If you'd like to learn more about the theory behind parameters such as power, distribution, or efficiency, feel free to check out the online documentation. In this final part, we'll take a look at mesh emitters. Mesh emitters, if you remember, allow an object to be used as a light source. The light generated by these emitters can coexist with illumination generated by other octane lighting systems. The setup is straightforward. What we need is geometry with an octane diffuse material assigned to it. Blackbody emission node and texture emission node should be loaded inside the respective emission channel. Let's close the picture viewer and take a look at how this actually works. What I want to do is turn these lamps into mesh emitters. But first I would like to reduce the influence of the default environment. To do that, I will use texture environment and will assign a dark blue color to it. Next, let's create a diffuse material and assign it to the corresponding geometry. I will use polygon selections to restrict the influence of the material. Next step is to select the material once again, and in the emission channel we need to use either blackbody emission node or texture emission node. Let's start with blackbody emission. Open it up, and if you take a good look, you will see that these parameters are pretty much the same as the ones we discussed with the octane daylight tag. we still have temperature, power, normalize, distribution and texture parameters, sampling rate and light path ID. If you remember, the light tag can work on the two modes, either black body emission or texture emission, and here we can control the same parameters via the black body emission node or via the texture emission node. Let's take a look at the parameters that are actually different. But first, just to make sure that Octane will interpret these lamps as separate objects, it is a good idea to assign an Octane object tag either to each object individually or to the parent of the hierarchy. Let's resend the scene, and there we go, the illumination now looks much better. Select the diffuse material, black body emission, and let's take a look at surface brightness. When this parameter is disabled, the brightness of the emitter will depend on the size of the emission area. Let's take a look at what this actually means. If I select a light and scale it up, you can see how the surface brightness is controlled by the size of the emission area. If, however, the parameter is enabled, and if I push the scale of the object up, you can see that no matter how I scale it, the brightness of the surface doesn't change. The next parameter is cast illumination, and it is self-explanatory. If I disable it, we still get the core luminant material, but the light that is being cast is actually cut off. If I enable it, we get the core luminance channel plus the illumination generated. This concludes mesh emitters.